So we have here another formal example that says show that v squared is equal to v naught squared plus 2a times quantity x minus x naught is true for constant. It doesn't say that there, but we're showing that it's true for constant acceleration. It doesn't quite roll off the tongue the way it's written there, I guess. But recognize that's the fourth kinematic formula, and maybe another way of writing it that we've seen, more abbreviated, was to use delta x here. For that last part. In other words, final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement would be a way of stating that in words. Maybe rolls off the tongue a little bit easier. I have a particular name for this formula. It is the fourth kinematic formula in terms of kind of my numbering system, but I also like to call it the timeless formula, because the thing that makes it kind of special compared to the other kinematic formulas is that the variable t is not present. And that's going to give us a little bit of a clue, actually, as to how maybe we could go about showing this. If we could maybe take two of the other kinematic formulas and do some kind of substitution that eliminates time, maybe this is what pops out. And that's basically the story. And I'm not going to write all the algebraic details on my board here because I have it all in the slide, and I think there's more than one way to actually do this algebra, but I've chosen a particular one. I think I started with the second kinematic formula right here, which really is kind of related to the definition of acceleration, but if you solve it for time, you get this. And then I've decided to plug that into the third kinematic formula. Another option could have been to use the first kinematic formula at some point for this, but I think this one is a more efficient option. And so what happens when you do that is here's where the plug-in for time happens. And what's kind of cool about this, I think this is kind of cool if you're into algebra, there's like a difference of squares situation here, right? You see I have like v naught plus v times a v minus v naught in the numerators of these fractions here. So naturally that becomes v squared minus v naught squared. So that's kind of that difference of squares thing you may recall from an algebra class. And then there is this 2a downstairs. So at some point, I think some more manipulations need to happen where we kind of set things up so we have this displacement, this what I call delta x up here on the left side there, and then you multiply by 2a, and that basically rearranges things into the final format. In that sense, you could say, hey, how come we didn't just make this the fourth kinematic formula? Well, physicists are a little bit aesthetic sometimes too, and I think at some point they felt that this type of a formula was more aesthetically pleasing to look at and use. This formula is also kind of like maybe a physicist's secret, because I've taught some math classes. I've helped students with math problems before, and most math classes don't include this formula. They would consider it cheating. I've heard of math professors even telling their students, don't use those cheater physicist formulas, and this is probably one of the big ones right here. I once had an experience where I was in the math lab helping somebody with something, and they had to set it up using function notation. And I looked at it and immediately recognized, oh, that's just a timeless formula situation. And then I realized, oh, shoot, I'm not allowed to tell them that. It was problematic. So this is our friend. Physicists like this thing. It helps us in certain situations where time is not given and it's very inconvenient to get to for motion problems involving constant acceleration. Hence, again, I call it the timeless formula as kind of like a way of reminding me that's where it tends to come up.